From the AI engineering perspective, there are a certain number of topics that we cover here in linear algebra that are going to be more useful than others. For example, PCA, SVD, and many others, eigenvalues, eigenvectors. In my opinion, cosine similarity is the one, in my experience, is the one that I use the most frequently as an AI scientist or an engineer. The reason is that it is very well defined between vectors. And since we use vectors as data representations, cosine similarity gives us a very well-behaved metric of um, similarity between these representations. So here we go. Let's see what cosine similarity is. Cosine similarity between the two vectors x and y is defined as like this, like what you see here. Here's an inner product in the numerator you see, and the denominator you see the norms of the two vectors that are being used. So if we take a look at this cosine similarity, first of all, it takes two vectors as inputs and it gives you one number. What is this number? It gives a number of how similar x and y are. First of all, if we take a look at what is going on with this operation is that, first of all, if you look at that, both x and y are normalized to be unit norm. So in a sense, when we take the inner product of the two, we are just calculating the inner product of two vectors that are on the unit circle, both of which have the unit norm. There's no, we are not talking about any magnitude right now. So what we get with cosine similarity is nothing but the cosine of the angle between them, because when you normalize them, it is the only thing that you have. It's not because just because of the normalization, it's because of the particular operation of inner product, which we will cover in week 3 when we're talking about the projection theory in detail. But long story short, the cosine similarity gives you nothing but the cosine between cosine of the angle between x and y. Plus, I would like to invite you to see that x and y is just not like two-dimensional vectors on a unit circle, but it's multi-dimensional. So think 12,000 dimensional. It's a hypersphere, hyper unit sphere, and the angle between them can be easily 90 degrees. But again, this is something that we will gradually cover. So the second good property of the cosine similarity is, obviously, since it's a cosine, it gives you some number between -1 and 1. And they become 1 only if they, or -1, only if they are just linearly related, only if they are living on top of each other, right? If they're perfectly aligned. And if they are just perpendicular to each other, in linear algebra we don't call it perpendicular, we call it orthogonal, then the cosine similarity gives you 0. So in the next slide, with a little animation, I'm going to give an intuition, a further intuition of what cosine similarity is doing, and a little application where it is used. Particularly, I used cosine similarities in FaceID, but right now, which I will cover in the lecture, they are mostly used in large language models for RAG, retrieval augmented generation systems, when we are very quickly seeing the relevant parts of a query or a question that's posed to a chatbot from a huge set of texts and get it as a context and answer the question, but I'll of course I'll not go so deep into how rag words but works in the lecture, but I will show you how cosine similarity is used in rag. But here we go. Before we calculate the cosine similarity, here on the screen you see the formula x transpose y divided by x norm and y norm, and I placed two vectors on this two-dimensional space, x and y. So here, first of all, what happens before I calculate the cosine similarity is that the x and y, when they are applied the new operation on the numerator, when I divide it by its norm, it just moves, it just scales. You see how it moves. So it goes to and places itself to the unit circle, because if you divide one vector with its norm, which is the definition of normalization. It goes and sits on the unit circle, and the other one also goes and sits on the unit circle. It just doesn't necessarily get smaller. It can get bigger if it is smaller than it's inside the unit circle. So these two vectors, notice how they did not move from their directions. I only changed their magnitude, and they're sitting on the unit circle. So they are both on the unit circle. So the only thing that separates them is the angle between them. So that's with cosine similarity, that's what we are measuring. All right, so let's move them back to where they were. And I'm going to go ahead and keep x the same and move y diagonally, and it's going to go and cross in front of x2. So as you see, as I move the x and y, the cosine similarity increases, and at some point when y is on, let me see if I can stop it there exactly, when y is on the same direction with y, with x, the cosine similarity value returns 1, exactly 1. It passes, right? So cosine similarity is a good metric to understand how similar the two. Of course, there are different metrics to measure the similarity between vectors. The most famous one is the Euclidean distance, right? So if the Euclidean distance is 0, then they're on top of each other. If the Euclidean distance gets higher, they're farther from each other. It is also used in linear algebra and also machine learning too. But cosine similarity, due to the property that they are, it gives you some number between -1 and 1, so that it's good for thresholding and building models that are going to be used later on. It is preferred. So finally, how does it um, how does it apply in FaceID? Right. So when we're talking about vectors or any kind of faces, we mentioned that the data is represented as data points or vectors on a hyperspace. Right now, our hyperspace is not such a hyperspace. It is a space, two-dimensional space. So let's say that we are talking about a face ID. We have the space, and the first goal of a neural network or a feature extractor, I use CNN here, but the machine that takes the images and then gives you these vectors on the space is not necessarily convolutional neural networks anymore. There are several other models, specifically vision transformers. But let's since we have been associating computer vision with convolutional neural networks, let it be, right? So I use this face of this person, and I placed it on a space. And another face of this same person goes through the convolutional neural network, goes to some other point. Okay, here I would like to pause. And okay, let me do another one. So this other person comes and places somewhere very close to the third one. the remaining two, and let me do another one that comes here, right? So what is this black box or red box that says CNN, and how it takes your image and place it as a dot on the space? That's something that you will cover. But uh, the more important thing here in terms of the Face ID is to make your black box or the red box, the CNN box, to take the image as input and images of the same person as input and place it on the hyperspace as points that are closer to each other, as opposed to taking the image of this guy and then, of course, placing it farther from that point. So, what makes it do this? Place the guy place the people of interest close to each other, or images of the same person close to each other and images of different people far from each other. That's the way it is trained. It is trained in a contrastive loss way, which is you are going to cover, but for the sake of this course, I would like you to trust me and believe that there exist such machine learning methodologies that can give you, or that can give you such a representation learning. That's the such a representation learning scheme. That's the terminology for this task. Representation learning, one of the most important conferences, ICLR, pronounced ICLR, um, International Conference on Representation Learning, particularly studies this. And representation learning um, uh, uh, is uh, the beginning of generative AI. So, like since you would like to type something that generates an image, what is this text converted into a representation, and this representation is converted into image, but we'll get to that. And this other guy comes, and this other guy is also far from the first cluster, and this other guy comes, he's obviously not the person of interest, he's also far. But the goal with the contrastive learning and representation learning is to have this some other image. Maybe this guy is has a cigarette and has a hat and a different color scheme, even though it is from visual perspective, even though it is a different X, we would like for it to place something close to the other cluster of our training instances, right? So how does this include the cosine similarity? If I were to calculate the cosine similarity of the three red dots to my cluster of training images, which you have all provided to your smartphones when you're registering your Face ID. If you remember, they want you to rotate your face a little bit. And here you go. You provide um, these blue, baby blue or white examples, and every single time someone tries to um, turn your computer on, they provide some image that gives a high, very low cosine similarity. Therefore, it's marked red and it does not turn on your computer or smartphone. But even if you're wearing a mask, hopefully, or some hat, it is close enough. It's high enough a cosine similarity that um, turns your computer or smartphone on. So that's one great application of cosine similarity. Inner product, and inner products are calculated very efficiently with digital hardware we covered so far. And that would be the end of week one.